so I'm just going to talk for the first few slides of this presentation to kind of set the scene. And then I'm going to turn it over to Becky and Kinsey, who are going to talk more about the meat of the project that we have been doing for the past, 5 years? It's quite a long time. So you can see that there's a cast of thousands associated with this, so there's probably more people associated with the project than are here in the room right now, but we'll talk more about that as we go along, and we have some pictures of them at the end. But just to give you a little background, just after I got here in 2013, the AAU, the Association of American Universities, put out a call for a proposed STEM education initiative. And this is a big deal because this organization, the AAU, is the major lobbying organization for many of the major R1 universities in the States and a couple in Canada. And the fact that they had turned their attention to thinking about education, it was the first time that they had, and I think that it got a lot of attention from people who are in positions to make things happen, like college presidents and provosts. And so MSU received one of the 8 grants that they gave to the 62 institutions. I think 48 of them submitted proposals. And we called it Creating a Coherent Gateway to STEM Teaching and Learning. And then just to follow up, in 2017 we got kind of a much larger scale grant to extend the work that we've been doing to a consortium of 4 universities. So MSU is the lead, then Florida International, Grand Valley, and Kansas State are also involved in the kind of proliferation of what we've been talking about. So we're now extending our Coherent Gateway, and funding came from MSU after that. And so I just want to show you what the AAU said about this. And what they wanted to do was to influence the culture of STEM departments, which is crazy, actually. And they gave these 3-year grants. They were $500,000. And if you know anything about the culture of STEM departments, you realize that this is probably not going to do the job. So, but anyway, we know that there is a fair amount of research on teaching and learning, both especially at K-12, but also in higher ed. And here's the Discipline-Based Education Research Report. Strategies are needed to effectively promote translations of finding. And so yeah, so we should do that. And how sad, this report is no longer posted on the
It uses only evidence.
because it uses evidence. There is no Council of Advisors on Science and Technology anymore, but just a happy memory. But they did put in their report the first 2 years of college are most critical, and we agreed. And so in our proposal, we did target the first 2 years. On our change model that we proposed, well, that we would build faculty consensus. And what we wanted to do was to develop a shared vision for the Gateway course transformations. And we chose biology, chemistry, and physics because those were the people who turned out at the meeting. And we also, there's a lesser emphasis, but also an emphasis. Obviously, we can't develop policies. We're a group of faculty. We can encourage policies that reward reform, but we did put in place a STEM teaching fellow network, which I'll talk a little bit more about in a minute. But the main thrust of our proposal was that we were going to develop a shared vision for gateway transformation. And to do that, we didn't actually use the research from the DEVA report. We actually proposed that we would use the framework, which everybody in this room, I am sure, is completely familiar with, and base it, and we proposed that we would adapt this vision of STEM teaching and learning for college classrooms. And that's our logo. Thank you very much. Thank you, Erin. And so our shared vision revolves about discussions. So that's what we did. We actually got faculty together in discussions to build consensus as much as we could on what are the core ideas, what are the scientific practices, and what are the cross-cutting concepts. And so that was the first kind of step in this project. And the result, we hope, is three-dimensional learning. All right, so I just put this up because I think everybody in this room is familiar with this, so I'm not going to go into it in great detail, but we have published on this now. We actually have a paper in Science, it's not on there, but never mind, where we proposed that we would do this, and that has got quite a bit of uptake in the literature. And so we've got scientific practices, we've got the cross-cutting concepts, and then to round it out, what we really focused on first with the faculty was the core ideas, because if we could get the faculty to think about and understand what the core ideas of the discipline were, then we might also get more engagement in how we were going to address connecting what we teach to the core ideas. So in biology, the core ideas, were developed by biology faculty, and they look very similar, but not exactly the same as the core ideas in Vision and Change, which is the AAAS project that revolves around the same ideas. Here is chemistry, so we used different core ideas than the framework. Everything else was the same, but we had to have our own core ideas. So these are the chemistry core ideas that we have been using over the past few years. And here's physics. All right, and these were developed by discussions among the disciplinary faculty in the departments. And the STEM Teaching and Learning Fellowship, essentially we have, I'm not exactly sure, but maybe 40, 45 faculty by now have gone through this program where we talk about core ideas, cross-cutting concepts and practices, where we apply the principles of backward design and evidence-centered design, because one of the things, as you'll see, is we're trying to focus on how we assess student learning, and then become part of this interdisciplinary community. And I know there are people in here who've been part of this community, and we are moving forward with that, and also now making it not only interdisciplinary, but also among the 4 participating institutions. So implementing three-dimensional learning, we believe that three-dimensional learning is going to change both how we assess students and the instruction that occurs in the college setting. So the question is, well, how are we going to assess outcomes? Because if you're familiar with any big transformation project in higher ed, typically the evidence that is proposed is not all that convincing about whether any transformation has actually occurred. So for example, the AAU actually suggested that we ask faculty, do you know about these evidence-based principles? And we actually did send that survey out, and you may have received it. But I had people come up to me and say, well, I filled out your survey, and I think I put what you wanted me to, but I don't believe it. And, so it's not very convincing evidence, right? Just because somebody knows about something or they say that they do it, doesn't mean that they do. So we decided that if we were going to do this, right, essentially it's going to lead to changes in classroom practice, and it's going to lead to changes in assessment practices. So we said that we would evaluate those changes. And so for measuring change, We could also collect the usual data, right? Persistence, grades, we could look at the effective domain, faculty perceptions. But we know that grades don't equate with learning. We know that, right? There's a lot of literature, the Deber literature, talking about how little students know. And yet students are still very successful. So that's not, we didn't believe that that was all that useful, but we should do it. And as I said, what faculty say doesn't necessarily align with the practice. So we're going to be measuring change by investigating classroom practice using a new protocol that Kinsey will tell you about. And also, we're also looking at the nature of the course assessments. So these two protocols, the 3D LAP and the 3D LOP, are the ways that we are thinking about how we will assess change. And so that's just the intro. Now we get to the meat.
So the 3D LAP is a protocol that essentially has two purposes. It helps us both, helps us and others so far, both characterize changes in assessments over time, but it's also been useful, and particularly here at MSU, it's been useful in the fellowship program that Melanie introduced for helping faculty think about, okay, if I have this assessment item, and here's the set of criteria that outlines, for example, how a question might reflect analyzing and interpreting data, blended with a core idea and cross-cutting concept, then why doesn't my question look like, why doesn't my question sort of meet these criteria, and what could I do to change my question to reflect it? So I think one of the best things that is in this paper is the supplementals, that is a long list of examples, right? As we were kind of coming to coding validity, or deciding on coding validity and reliability, we were looking at, we were binning all of these different kinds of assessment questions that we could come up with and say, this isn't, and why and why not, and so forth. So there's a long supplemental that has that in there. So one of the papers that has come out that that some of the chemists put together was looking at that first purpose of helping faculty basically adapt assessment items. And this is a JChem Ed, right? It's kind of targeted at a practitioner audience. A JChem Ed paper focused on how can I look at my original task and sort of filter it through the 3D lab to make it something that might elicit some evidence of students engaging in the dimensions. So that came out just this year, last year. This year, 2018. So for example, a traditional item might ask students to look at a reaction and calculate the enthalpy change for that reaction, so essentially the amount of heat absorbed or heat evolved from that reaction. This is very typical. Some of my favorite examples of the traditional assessment items were these kind of like, almost like rule-based, like if you have, add the number of electrons in this atom to the number of protons in this atom, and multiply it by this, and then tell me what you get out at the end. And so there's all these different kinds of skills wrapped up in a question like that. And at the end, if a student doesn't get it, you really don't know why they got it. And sometimes even if they get it right, you might not know really why they got it. So different kind of example. But this is pretty typical, and not just typical here, I think it's typical of a lot of kind of general chemistry classes, courses, different universities. So an example adapted item, we found, it's easier to get into students' heads, right, when we can get them to construct their responses. And so a lot of times it was easier to identify or adapt items that were three-dimensional when they were constructed response. And so in some cases we ended up, sort of adapting items by taking a typical sort of selected response item and making it, a richer kind of almost activity in some cases. But not always, not always. This is one example. So here, the first three subparts ask students to draw the chemical structures for these reactants and products, and then to identify in particular which bonds are broken and which are formed, right? Because sometimes students like to think, oh, I'm just going to pretend that like every bond is broken and every bond is reformed, but like that doesn't really reflect what's happening in reality. And explaining why breaking bonds requires an input of energy from the surroundings. So we could see that as constructing a model or constructing an explanation there, and using energy embodiment interactions. Then the second part D there, is asking them to do this sort of like rote mathematical work of calculating the enthalpy change, right? That's essentially all that is occurring in the prior example. And then using that calculation to construct an energy diagram for the reaction, right? So they're using that mathematics to do something. So, right, so that knowledge of that enthalpy change is actually helping them construct something that helps them understand the reaction even more. And then the last part, constructing an overall explanation for why the energy change in the reaction is either endothermic or isothermic, and what's the evidence now that they have to make that claim. So we would see this as a richer and three-dimensional example. So this would be like an example of something that we coded. I'll show you some data in a moment where we were coding lots and lots and lots of exams, and this would be an example of something that we had coded this three-dimensional, whereas the prior question we would have. So when we developed the 3D lab, one of the things that we did was just test it against exams from traditional courses and exams from reformed courses and see what we could see, right? Did we see any signal with this protocol or not? So this was an iterative process, right, of looking at exams, of refining our criteria in the protocol, looking at more questions, and also reconciling across biochem and physics. So the data that I'm going to show you today are primarily from chemistry, but it was also a process where we were, aligning ourselves between biochem and physics throughout the whole process. So each of the tables here is representing an exam. The top one is a traditional, just by question number, the bottom one transformed. And indeed, we could see, after many rounds of discussion and like many years of discussion, actually, that we could reliably identify across the disciplines whether an item had or didn't have assigned reflected practice or cross-cutting concept or a core idea.
So hang on, Becky,
Yeah.
for a second.
Oh, I don't know how to go back. Okay. Yeah.
So the top thing was in MSU courses, there were a grand total out of 20 questions, 5 that had any core idea and none had anything else.
So mostly skills, right? So one of the things that we did in the project was kind of identify, like, what are the skills that occur that regularly show up in a discipline, like drawing a Lewis structure, or calculating formal charge, or maybe doing a Punnett square in biology, or like drawing a free body diagram in physics, right? These are things that like are very, very, very useful tools. Sometimes you want to assess them, right? Like you don't always want to assess like this giant sort of like collection of like skills and knowledge, but sometimes you do want to do it. But they appeared to be very skill heavy, right? And not just in bio, but or not just in chem, but in bio analysis also. Yeah. So this was, I'm going to walk you through a table here. So we ended up coding for this project. We basically collected exams. We begged, borrowed, we didn't steal, begged. We didn't actually borrow, we just begged. I begged a lot. And Melanie did too. Asking faculty if they would allow us to look at their exams. No student work here, this is just the problems themselves. We solicited their final exams, and when those either weren't appropriate for some reason, or they weren't available for some reason, or they just didn't want to give them to us, we asked for their midterm exams. So, we're looking at the high stakes exams that are occurring right now in intro bio, intro chem, intro physics. So if you look at that we called it the beginning year, year 0. Year 0 was the year prior to the AAU project beginning, and then we continued to collect them for 3 more years after that. So it was like really, it was crazy. It was crazy. So we split them out. We have them grouped by discipline, except that we split Bio 1 and Bio 2 separately from each other. And the reason we did that is because the faculty tend to cross Bio 1 and Bio 2 not as frequently as they do in chemistry, right? So chemistry instructors tend to teach Chem 1 and Chem 2, or Chem 2 and Chem 1, or they mix around and do both. But there's much more, they're much more siloed, for lack of a better word, in Bio 1 and Bio 2. So that's why. So this is how the data are presented. So Chem 1 and 2, Physics 1 and 2, Bio 1 and Bio 2. And the point of this table is just to show you that there's sort of lots of different ways of like asking, well, what are we interested in, right? Because some instructors teach multiple sections. Sometimes multiple instructors use the same exam. And so we kind of had to get down to the level of like, what are we actually talking about? We're talking about the exams, right? And then figuring out how many students are seeing those exams. So there's a variable number of course sections, a variable number of unique instructors. a variable number of unique exams coded, right? Sometimes faculty would use the exact same exam in year 1 and year 3, and we didn't, if they were literally the entire exact same exam, then we wouldn't code that exam a second time. So one of the things we did in terms of, so how do we get to that 4,020 number? Oh, there it is, look at that. Okay, so obviously, we coded things as either individual questions or clusters of questions, so that clusters being like those multi-part things, right? Like use this diagram to answer the next 6 questions. Okay, well, if you're teaching 400 students and you want to ask them about sort of a larger idea, you might break that up, to facilitate grading or whatever. And so we tried to give, the exam authors basically the benefit of the doubt by saying, like, we're going to consider that all one question, right? And we're going to give, say there's a 6-part question or 6 multiple choice questions that rely on one diagram or something. Then we would say, we're going to consider that a single cluster and we're going to code it all together. So we're going to consider that holistically, essentially to give everybody the benefit of the doubt, recognizing like the constraints of working at a giant university. If we had the same particular question used like a single question, showed up different times on multiple exams, then those questions got coded multiple times just because reasons. We can talk about more if you care about that. One of the first things we did was, like Melanie was saying, we used some of these kind of traditional measures of showing what happened. So essentially, do no harm kind of approach. So one of the things we looked at was mean final course grade and DFW rate, or D grade, F grade, and withdrawal rates all put together for a given course. So for Chem 1 and Chem 2, that's the orange data. Oops. Oh. Okay. So you can see project year along the x-axis, and you can see the DFW rate, which is the triangles, decreasing pretty dramatically, and the mean final grade also increasing, still with a big spread, but increasing rather dramatically for a course that is looking at somewhere between 3,000 and 4,000 students every year. Like, this is a really meaningful change in the gateway sequence, in the gateway series for like a huge portion of MSU students. So, so snaps to all the chemists in the room who really facilitated this. So students had significantly higher final grades in year 3 than year 0, and this practically translates, like right now, there's about 750 students, 750 additional students who will get a 2.0 grade or above in one of these courses than they would have 5 years ago. That's like, I just got the chills actually. It's kind of crazy. So what happened in terms of the exams, actually I probably should have showed this slide first, but what happened in terms of the exams in chemistry, again this is just particular to chemistry, so each data point here is an exam, right? And the size represents the number of students who are taking that exam. So chemistry has common exams, all right? And so all, X hundred students are taking the same exam, and so their bubbles are very large. Bio, it's different. I'll show you a slide with the bio data and the physics data soon, and you'll see that it kind of varies depending on the discipline. So there was sort of a wholesale change in chemistry, right? They were shifting curricula. They were completely shifting curricula. That didn't quite happen in bio. This is sort of unique to chemistry in the project. But we did see this increase for chemistry. There's our chemistry data again, just a little bit smaller. Here's our bio 1 course here. It's bio 161. All right, so year 0, we see, again, so you're going to see more bubbles for bio 1 because there's no common exams. So you see in year 0, we didn't really see any questions that sort of would help us elicit this evidence of three-dimensional learning. And then there was some movement to varying degrees in different sections, depending on, maybe some of the instructors were fellows, maybe some of them weren't, but they were toying around with changing their exams or doing something different anyway. So that's what the bio 1 data look like. Bio 2 looks pretty relatively flat overall. And I think there's good reason for this. Bio 2 has had a lot of activity occurring around it and in it from some dedicated faculty who have been really working on incorporating models, arguments, and data and collaboration into the course since like 2008 or 2009. So it wasn't that surprising to see them already have kind of a spread at year 0. And you can see there's there's a little bit of movement maybe towards year 3, but no statistically significant differences between 3 and 0. And then physics looks like this. So physics is sort of flatlining a little bit. Physics has these kind of little glimmery sections up here in years 2 and 3, which were also new curricula kind of experimental pilot sections that actually now, as far as I know, are kind of getting some more traction and seem to be moving. They seem to be moving more students into sections like that in this year and in the coming years. So that's it. We have a whole this data and a whole bunch of accompanying data just got accepted into Science Advances, so you can see it soon. I'm definitely not checking for the proofs every day at all. Waiting for them. But there's more underneath this. There's more. This is the tip of the iceberg, and there's more. If you're interested in more, we can discuss.
Like Becky said, the assessment protocol has been developed and utilized in many different ways. The observation protocol has taken a little bit longer to get off the ground, so that is my primary role here. And so again, this protocol has a similar purpose to look at this change over time that's been occurring here and soon elsewhere at other institutions. But it also has a secondary role, which would be to help faculty improve their instruction. And so we're kind of in the thick of trying to figure out what are the features and criteria that should be included in this observation protocol, and I can kind of show you some of what that looks like at a more detailed level. But you may be first wondering why we're making up our own protocol. So when looking in the literature at other protocols, many of these other protocols are looking at the how and the who of what's happening in classrooms. They're looking at the instructors and the students and the interactions, talking about active learning, things like that. But not many of them are looking at information about what is being taught. And that's really what we want to think about, is the content, what the content is, and how it's being used, and how it's related to other courses and other disciplines. And so the initial development did look at many of the hows and the whos, as well as the whats, and it looked somewhat like this, and I'll show you a larger version in a second. But if you look up here, it's kind of hard to see. So there's lots of little blue boxes, and those are trying to just kind of show when a clicker question happened, or when there was some kind of specific interaction, or if there was lecturing going on. And it's more of a timeline piece, but at the bottom, the purple and the red are trying to kind of get at, is there a phenomenon being discussed? Are there core ideas, science practices, those sorts of things being discussed? And that is where we're really wanting to focus, and we've kind of moved to mostly just considering that portion, and I'll show you what the new version of that looks like in a second. But if you look at the top of this, it looks like a very active classroom. There's a lot happening. It's not all lecture. There's lots of questions, different things being elicited from students. And so if you had something like a COPUS or some other observation protocol, this would look very impressive. But if we are looking at maybe the core ideas, those red boxes at the bottom, there's really nothing happening. There's not many instances or any instances of science practices or cross-cutting concepts. And so that's the direction we've moved, because that's what we're here hearing about. So what we've done in our current iteration of this observation protocol is to first take the videos and try to figure out what our unit of coding will be. In many of these other protocols, they think about things maybe every 2 minutes or every 5 minutes or some sort of number interval. And that wasn't really working for what we were trying to do, seeing as many of these things kind of have some sort of like build up to whatever you're trying to do in your classroom. And those weren't really allowing us to capture kind of a build up to engaging in a science practice or a core idea. And so we moved in a direction to creating what we call chunks, or segments or sections of a class period. And we've done that now for all of our videos, but we've tried to kind of think about the videos in terms of chunks that center around a specific topic, not necessarily a core idea or a practice, but something that could stand alone as its own unit. You could maybe stop there for the day as an instructor and pick up the next day, and they're related by content always. So this would be an example of a timeline for a class period. And if you look at the start, this gray box over here, that's just the first 5 minutes of class that often appears to be what we call an administrative chunk, where you're just talking about things that have happened or are about to happen and just kind of getting your class on the same page. But these other chunks are chunked by content, like we said. And so the first couple are specific homework review things, where they're centering on some things that happened in the homework and kind of debriefing on those things. And then we have a dilution of solutions. We have a big activity here, and then another activity that are somewhat related but discrete. So they were pulled apart. So as you can tell, this was a chemistry classroom. We're talking about dilutions of solutions, exothermic dissolutions, endothermic dissolutions. So practically, how are we coding this? This is kind of just the first step in what we're doing. We're trying to think about the 3 dimensions, as we've said before. And we're starting first to think about, are there science practices being demonstrated? Those seem to be the easiest to spot, and so we've moved them to the forefront. They're also really important for doing what we want students to be able to do, which is to practically use their knowledge. And so we're starting first by coding for that.
Quick question.
Yes.
So science practices demonstrated or engaged in, or both?
Both.
Okay.
So that's exactly kind of what we've got here. So here's just one of the science practices, developing and using models. So thinking about the instruction as presenting an event or a phenomena, and that could be for the instructors or the students or both to be engaging in. And that kind of instructor or student aspect appears in pretty much all of these criteria. So if we've got some sort of phenomena, then they're asked to either construct or use a given representation, and then to go on beyond that and provide reasoning that links the representation to their explanation or prediction. So these would be the criteria for that specific practice, and we have criteria for other practices in a similar manner. We're also coding for instructor versus student. So we did say we don't really want to be categorizing all of the different things that are happening in terms of how the class is being conducted, but we do want to know who is doing that engagement. Is it the instructors, is it the students, or is it some kind of blend in the middle? And we're still kind of trying to define what all those different categories mean. So that's not the primary purpose of what I'm talking about right now, but that is something we're trying to tend to, because that is a really important piece. And then moving on to thinking about whether or not there's a core idea present, and then a cross-cutting concept. So for example, if we have the same timeline for this chemistry class I presented, this was the coding that came out of it. So it's a little overwhelming, but this first row here is science practices. So pretty much most of the class period was engaged in a science practice. 4 of the 5 content chunks had practices. Some of them seem to have more than one practice, which is debatable among the group, but there is or is not a practice. And then 3 of those 4 went on to also have core ideas in those chunks and cross-cutting concepts as well. Again, the specific core ideas may be many in number, or we may be debating them, but there is at least some kind of core idea present, and that's mostly what we're worried about at this point. So if I zoom in on that really long chunk right in the middle, I said that that was an exothermic dissolution activity. So what was happening in the classroom? So I've got a few screenshots to kind of help guide you along what happened and what led to the coding that you see here on the left. So in the classroom, calcium carbonate was actually put into baggies, like sandwich bags, as well as some water. And TAs walked around and actually let students feel what was happening while the dissolution was occurring in this bag. And so students were able to actually kind of feel and somewhat engage with that, the macroscopic portions of that phenomenon. And then they were asked to think about this dissolution and draw a picture of the calcium chloride solid as they conceived of it in the solid state. And so then they were given time to do that. TAs and instructors were walking around, helping them think about this and scaffold some of that. And then they were brought back together as a whole class to kind of debrief, discuss, elicit some of the student responses, and kind of come to a classroom consensus. Then they were asked to do the same thing, but now think about drawing a picture of calcium chloride as it is in the aqueous solution. And so then they did that in their small groups, or with their TAs and their instructors walking around, and then they debriefed again as a large group. And so if we go back to our developing and using models criteria, they did have a specific observation or phenomena that they were trying to explain or make a prediction about, but here is more explaining. They were then asked to construct representations of what that looked like before and after the dissolution. And they were asked to actually, in their large group debriefing sessions, provide reasoning that linked that representations with their explanations of what they saw happening. So we've been doing this for a while. We have actually successfully chunked all of these videos that we have, which is over 180 of them, and we're collecting more. But we're in the process of now trying to demonstrate some fidelity in the coding across our large team. If you remember our title slide, there's many of us. So we're trying to kind of calibrate one another to coding the same way, and then scaling that up so that we can do similar things as we did with the assessment protocol. Try to see if we're making changes in the classrooms in the same way that many of the assessments have made change over the past 5 years or so. As well as then use it as a professional development tool with our STEM fellows as well. And some ongoing research questions that are beyond the scope of this talk is thinking about how are the faculty applying this framework in their courses, but also how are those barriers to adaption addressed. And so we're doing some faculty interviews, thinking about things from that perspective, because the different disciplines seem to uptake these changes differently, what's going on there. So that's a whole different side project. And then thinking about how are the outcomes for students. We talked briefly about some of that, and we've been collecting that data, but that's something we also need to dive further into.